The following content has been provided by RWTH Aachen University.
First of all, you've got your sequence of physical interactions, right? So homing, pointing, clicking. You then insert, initially, M's almost everywhere, like in front of all the keystrokes and in front of all the pointing commands as well. If the pointing is there to select a command, what does selecting a command by pointing mean? Well, it means clicking on a button that triggers an operation or selecting a menu item that triggers an operation. That's selecting a command by pointing. But not if the P, the pointing, is there in order to select an argument for the command. So then you've got lots of M's thrown into your sequence of elementary physical operations, and then you take them away again. The first ones that you take away are the ones that are anticipated. What does that mean? If, for example, you are trying to point and click at something, then you are not going to stop in between pointing and clicking to have that mental operation. Right? You might do that afterwards to verify that you did the right thing, but not in between these two. The pointing and clicking basically merge into one thing that happens right after each other. So the M goes away. We say that the second operator is fully anticipated by the first one. It's basically one gesture that you do in one go without stopping to think. Second rule says that you also take away M's within so-called cognitive units. And that would be, for example, when you type the command ls on a Unix terminal just to list the contents of the current directory, it's ls enter, right? So in a string of these keys, like the L and the S, you don't stop between the L and the S to verify that you did well so far, at least not in this measurable sort of 1.35 seconds. You just type ls as one command. No, we're not talking about the return key yet. That's going to come up in a second. So here you take away, usually you would have mk, mk, mk for each of these three enter characters here, L, S, and the return key. You take away the middle one because you don't stop in between the L and the S. Next one, you take away M's before consecutive terminators. That would be if you have to, for example, type this blah and then two return keys, you're not going to stop between those two return keys. Those are both delimiters that are consecutive, so you take that M away as well. So that's why it's missing in between here, right? So that one goes away. Fourth rule says, take away M's that terminate commands. Note that we're not taking away M's that terminate arguments. Why? Because commands become muscle memory. If you've been working on a Unix terminal a lot, typing ls and then hitting enter is one gesture. You do go like ls enter. You don't even think about it. You don't go like ls, oh, is that right? Enter. So that's why in this case, not only do we remove the middle one from the rule number 2, I think, but we also take away the one right before this one. But we don't do that if the thing that comes before the delimiter is an argument or a variable string that could be different. So if you type, ls and then the name of a directory, then we would, and then hit enter, then we would still leave the M in there because you're probably going to be verifying the directory name that you got that right, especially if you think about it being like a delete command or something. And then finally, if M's overlap with anything that is a response from the system, you take that away too. Which again makes sense, because if you are verifying what you just typed while the system is busy computing something and not letting you continue typing anyway, you're both working at the same time. So we're not going to count that in sequence, but we're going to notice the parallelism of those two things, you thinking, the system thinking, and that's time that is only basically wasted once, not twice. OK. This is a little weird or a little abstract, so we're going to do a little exercise here. So you'll need a bit of pencil and paper out. The idea that we're going to be using the next couple minutes as an example, running example, is there's a guy sitting in a biology lab And he has a pretty, he's looking after technology, but he also has a pretty sad job, which is if anybody in the lab needs a temperature converted, they're going to just yell that over and say, like, hey, Bob, how much is 35.6 degrees Celsius in Fahrenheit? Okay? So he gets these things. So he sits there at his computer and has these conversions to do. And he needs an interface for that. So the temperature converter we're going to implement is going to convert between Fahrenheit and Celsius, or vice versa. And we are now going to make a couple of assumptions about the use of this tool. Like what kind of numbers are going to come up, what kind of interactions are going to be coming up, how often. And we need to make these assumptions so we can compute our KLM model. So the assumptions hopefully are somewhat realistic for the task. First thing is we assume that requests are equally distributed between one direction and the other. So 50% Fahrenheit to Celsius, 50% the other way. The user can use, Bob can use his keyboard or mouse at will, in a mix, whatever, to enter the temperature and to do the conversion. We're totally flexible as to the input device here, mouse or keyboard. We also assume that this window of the temperature converter is already in front of the user. So Bob's already sitting there. This is the active window. He doesn't have to activate it or start the application or something like that. We're assuming he's doing this obviously on a desktop computer or laptop or something, not a multi-touch device or mobile device. And we assume also, for now, that we have an average of 4 typed characters to enter the temperature, including the decimal point. That means, sometimes it's going to be only 10 degrees. So type like 10. That's very short. Sometimes you might have, 52.87. So that's pretty long. But we assume that most of the conversions are going to be, on average, 4 characters long. So for example, 30.7, 30.7. That's 4 characters. We even include the sign in this. So sometimes something negative might come up, maybe like minus 7.5. Then you have like minus 7.5, also 4 characters. So you notice we're already simplifying because that's not precisely the reality of the numbers that are probably coming up. You would have to actually measure that and test it, but it's a good estimate. We also, to simplify this, we assume that there's going to be no typing errors doing this, just so that we can get an idea of how fast it is. As you know, the keyboard typing routines already include immediate corrections, like the 0.2 seconds for a keystroke already includes some immediate, oops, wrong character corrections. So your task is to go ahead with your partner sitting next to you and come up with a simple UI that will do that, and then figure out how long it's going to take. So the task should be clear, Celsius, Fahrenheit, and vice versa. Design a little dialog that will do that when it's in the front of the, and has the focus. And I'll show you again the rules for placing these M's. They're actually on 2 slides, so it's a little difficult to see, but these are fairly obvious. You remove anything fully anticipated between 2 operators, and you remove the ones within cognitive units, like simple words. So I'll leave these up here. These are a little more complicated. So we'll have a couple minutes, sketch an interface, and figure out how long it's going to take to do a conversion, okay? So in 50% of the time, since they're equally distributed, we won't have to press that button. In the other half, we do. So if we do need to change the conversion direction, or let's maybe look first at the one where it's already selected, because then it's easy. We just have a mental prepare that actually stays there. Then we set on average 4 keys to press to enter the number. Right? Average is 4 key presses, no matter it's a minus or decimal point or whatever. And then we have a mental prepare in order to, in front of the last one, because that is the button you press or the key you press in order to start the conversion. And that would add up to 3.7 seconds if the right direction is already selected. If we do need to select the conversion first, it's a little more complicated because we need to move the hand over to the mouse. We said that the hands are on the keyboard to start with. Right? That was the starting condition. So we have to have a homing happening. We need to point to the desired button and click on it. That's a homing, pointing, and clicking. Now we move the hands back to the keyboard, type the 4 characters, and tap Enter. So in addition to this one, we get the second homing operation, 4 keys for the number and the Enter key. Now by rule 0, we insert a bazillion of M's into this, which makes it look somewhat like this. So we got M's in front of all the K's and P's. And then we take away a lot of those. We'll see we take away the anticipated ones. So those were the ones where we said rule 1, we remove a lot of the ones that go away. So this one here is the point immediately followed by a click. That one goes away. Rule 2 says remove the M's within cognitive units. That would be, in this case, the number we enter. We've got like minus 7.5. You don't stop after each digit to type that. So these go away. And then as a result, we have this, HMPK. So 1 mental preparation for the homing, for changing the direction, and 1 mental preparation here to enter the data, and then finally the one that closes the interaction. That gives you an estimate of 7.15 seconds. So over 7 seconds. If we average this, 50% these, 50% these, we get to 5.4 seconds on average as a rough estimate of how long it's going to take to do the conversion. We're going to come back to this a little later and going to improve that design a little further because you can already see there's a lot of time wasted going back and forth between the keyboard and the mouse in doing this. And we're going to look at how good can this get. I'm going to actually give you an upper limit, or if you like, a lower limit of how fast you can actually theoretically get if you designed the best possible interface that you could think of. Yes?
Don't we need an M at the end to let the user check the result?
No, the M is there to verify that I entered the right thing, and then the interaction itself is done. I mean, yes, there's probably going to be, all right, the result is whatever, 14.7, and you're just going to yell it over, hey, Max, the result is this. That's when he uses the result, but we're not measuring that. You're totally right. That will be part of the larger interaction that's going on, and it's something to consider when you design the UI. But just for this analysis, just to see how long does it take until I have the result in front of me, then you don't look at that. Also, because I guess looking at the result and evaluating it for whatever purpose is not a routine task, right? It's something that maybe I just need the result and write it down or enter it somewhere else. Maybe I need to tell it somebody. We don't know yet. We're not looking at that. So before I get to these improvements and the theoretical optimum we can estimate, let's quickly look at what we have so far. When you do GOMs, what do you get? You get execution times. And remember, this is important. These are execution times for trained, routine users for repetitive tasks. So not something where they scratch their head a lot and go like, what am I going to do? So the tasks or goals, to speak in the 7 stages of action, are very well known. You're basically doing it as fast as you can. You don't need to think about what you're doing anymore. What this gives you is the execution times, and in some of the variants, like the natural GOMS language, you also get learning times, but we're not going to go into detail on that. You basically get because you now have times and time spent doing on a task, you can convert that to dollars, euros, yen, whatever. And knowing that the cost of daily use or the cost of training can be estimated is a big one if you are trying to make a case in a business setting for a change of a user interface into one direction or the other. Some models also give you an idea of errors, so that's also a nice thing to get out of this. And the good thing about this is that you are now able to link your costs to other costs. For example, if you say, we're going to spend that many hundreds of thousands of dollars to change our system to a new version or install a new software or buy a new software, but it's going to save us that much time in interaction times, which we can now convert into money, basically, because these people that sit in front of the computer wasting their time are paid at a certain rate, then you can start arguing why it might make sense to actually make that investment. And that's always a hard thing to do. As a user interface designer, you always are pressed by management and other people, customers, etc. What's the payoff? If I spend that much money on you helping me with the user interface design rather than just letting my engineers go at it, what am I saving? What's the benefit, the financial benefit? So this is one way of making that financial argument. You can use it to model alternatives. So for example, Ninex was a phone company that was offered a new system for its operators that had a great graphical user interface. This is back in the days. But they used a variant of GOMS that also took into account parallel activities to find that the new system would actually have cost more than the old system. $2 million a year in wasted time of their operators clicking around with the mouse when they were currently using a system that was much faster by doing keyboard operations. So another thing you can basically find out with this is, if I, for example, spend so much money on training, which is again, it's intangible of what the benefit is, you can say, well, training will speed people up by, from our experience, by this effect, and that will save us long-term cost in training, in work time savings. It's also a great point of starting to write documentation. Why? If you think about the simple GOMS model we saw last time, where we said, like, what do I have to do to enter a piece, or to highlight a piece of text? Click at the beginning, and then move the cursor to the end, and shift-click again. That's basically a manual, right? That explains how to do selection. So a good GOMS model, if you have especially if you have this tree of the standard GOMS model, not the simplified sequence of the KLM GOMS model, also gives you a starting point for documentation and tutorials. Remember not to use this for casual users or completely new user interface techniques that you don't have a modeling of the operators for. So if I design an interactive exhibit like we've been doing in our lab every now and then, where a user comes into a museum and starts using an interface to, I don't know, learn about Aachen's history or something, that's not something you would model with GOMS, because it's not a routine task. He's not going at it as fast as he can. Right? He's discovering the interface, using it for the first time maybe, so that would not be a good use for GOMS. Or if I had to model a system that used in the air, in the air gestures with a connect or something, and I don't have any idea what the basic operations take in terms of time, I can't build a GOMS model of a task because I don't know what the basic operator times are.
This content was provided by RWTH Aachen University.